I have here some radioactive things. I'm just curious. This is a neat thing. It's a wristwatch. This is a wristwatch here. Nicely radioactive. This was purchased by one of our assistants. He went to a flea market looking for watches that glow in the dark. Found a really old one. He bought it, donated it to us, and now I demonstrate it as one of these infamous radioactive wristwatches. This wristwatch is one that I would not wear. I don't mind holding it for a little while, but I wouldn't wear it regularly. It's too radioactive. How radioactive is too radioactive? Yeah, it's about too radioactive for me. It's radioactive because the arms are painted, the hands are painted with radium. Radium was one of the first radioactive materials discovered by Madame Curie, concentrated and purified by her. And they got it so purified, it glowed in the dark. If you've ever seen the movies or read the books about Madame Curie, there's a time when she and Pierre go and they see this thing glowing. Why was it glowing? What's going on? That's the sort of thing we're talking about today. Here's another radioactive thing. You know what this is? No, it is not that. Okay? I have to put it by the microphone for you to hear it okay. This is what's called a gasoline mantle. Those of you who go camping know there's a kind of lamp you can buy in which you put this thing inside of the lamp and then you flame it until it's just a little ashes are left. And then you let gasoline go, and it acts like a wick for gasoline, and you light it, and it gets very bright. If you're ever at a camp spot at night and someone a mile away has this bright light that's bothering you because you wanted to pretend you were all by yourself out there and you can't because this jerk a mile away has lit this lamp and therefore your pretending doesn't work, it's one of these things. And you'll notice it's rather radioactive. Why is it radioactive? What does that have to do with the fact that it is bright? It turns out nothing. It just happens to be radioactive too. What they do is they soak this thing in a salt of thorium, and they do that because when they do it for the same amount of gasoline, you get more visible light out. So it's a way of making it more efficient. It just turns out thorium is radioactive. That has nothing to do with it. What is radioactive? What are we talking about here? Different kinds of radioactivity here. You listen to this thing and you say, hey, Muller's a little bit radioactive. Is that because of his radioactive watch? I love my radioactive watch. This thing has tritium in it. Tritium is my favorite radioactive material. The arms are loaded with tritium. I go out at night and I want to know what time it is. Pitch blackness in the middle of the Sahara Desert, and I go, oh, it's bedtime. Okay? When I'm sleeping at night, if I left my watch on, and I say, I wanted to get up at 7 a.m. tomorrow morning, I wonder how many hours of sleep I have. Oh, I still have another 10 minutes. Good. Because my watch is glowing even after 16 hours in the darkness. Most watches have either a button you push that you can see at night to turn them on, and that's basically a light bulb, or they have something which, when it's exposed to sunlight or ordinary light, the chemical picks up a little bit of energy, and then it will glow for a half an hour or so. But then it's lost all that energy. It only picks up so much sunlight, and the chemical gets into what we call an excited state. We'll talk more about this when we get to quantum mechanics and atoms. And then it emits light, but that dies away. Not this radioactive watch. It keeps on glowing. This watch will glow for 10 years, brightly. I wouldn't wear this watch. What about this watch? This watch? This watch? Ah. I wisely picked a different kind of radioactivity. I picked a radioactivity that doesn't get out of the watch. Radioactivity is like fire. It's dangerous. I have a friend who, I was hooking up wires to my high fidelity set, and the friend said, oh, I'd be afraid to do that. Why? Because it's electricity. So I asked the friend, well, would you put batteries in a flashlight? Friend said, well, yeah, but it makes me nervous. Electricity kills. And if that's all you know about it, then you're scared. It's like fire kills. And most of us have some experience with fire. At least we use a gas stove. And we say, oh, that fire is okay. It's the fire in the house you don't want. How about the fire in the chimney? Well, that's okay too, but you want to be extra careful with that. So you have some idea and appreciation of fire. I want you to have that kind of feeling and appreciation for radioactivity. And that's what we're going to be doing today. We're going to be talking about radioactivity, what it is, when it's bad, when it's not bad, when it's your friend, and when it's your enemy. And it's like fire. And the more you know, the more effective a person you can be, whether you're just a citizen or president. And it's become even more important these days because radioactivity, once again, is in the news. Two things that you see very frequently in the news these days are talk about nuclear weapons in the hands of terrorists, radiological weapons. I want you to know what a radiological weapon is. A nuclear weapon and a radiological weapon are two different things, although they may be. So they're all. I mean, sometimes it's hard to tell which one is which. In a nuclear weapon, you use the energy of radioactivity to make an explosion. Now, the radioactivity gets spread around, and that can do some harm. In a radiological weapon, the main thing you're doing is spreading the radioactivity, whereas in a nuclear weapon, the main thing you're doing is making an explosion. So we'll talk a lot about this difference. And you see fear of radiological weapons. Well, the terrorists are going to get a hold of radioactivity, and all they're going to do is put it inside a TNT bomb and blow this up and spread radioactivity over the city so nobody will be able to go back into the city. And I want you to really understand this, because that radiological weapon is one that's in the news, and there's an enormous amount of misunderstanding about it, just as there's an enormous amount of misunderstanding about nuclear weapons, about nuclear reactors. These all are things having to do with radioactivity. So let's first get some definitions down. What is radioactivity? What is radiation? The terms are actually used by scientists differently. Radioactivity refers to the fact that inside certain atoms, there's an unusual kind of explosion that releases 1,000,000 times more energy than ordinary chemical explosions. Typically, in an atom, you might have, well, for example, when you burn hydrogen, what you're doing is taking a hydrogen atom and two oxygen atoms, I'm sorry, two hydrogens and one oxygen, and these two things will come together, and they will form a water. So two of these and one of these come together, and they form H2O, which is water. Looks like Mickey Mouse. And in the process of doing that, the energy of attraction bringing these together gets converted into heat. And that's the heat that you get when you explode hydrogen. So this is ordinary chemistry. And I'm going to use a new unit for this, because when you're talking about chemical reactions, the typical kind of energy is about 2 times 10 to the minus 19 joules. Remember, there are 4,000 joules in a calorie. No, I don't want you to know this number. It's tiny because an atom is tiny. And to get a big chemical reaction, you need zillions. You need like Avogadro's number of atoms to have something you can hold. And so if you have 10 to the 23rd atoms, 6 times 10 to the 23rd atoms, then even a little bit per atom adds up to, to a cheeseburger. So the energy per atom is small. It's like this, 10 to the minus 19 joules. Multiply that by 10 to the 23rd atoms per fist, and you wind up getting a number of thousands of joules, which is like a calorie. So the energy per atom, of course, is small. That's because atoms are small. But this has a new name. We call it 1 eV with a capital V. That's a name that we're going to use this a lot because when you're talking about individual atoms, it's nice to have a unit that's like 1. So this is called 1. It's called an electron volt. And the reason it's called an electron volt is that's the amount of energy that a single electron has if you put it on a 1-volt battery. So it's called an electron volt. But right now, just think of it as sort of 1 unit of chemistry. Now, in addition to these kind of chemical reactions, which involve the different atoms colliding with each other, sticking and turning that energy of stick into chemicals, so there's hydrogen and there's oxygen. You get 1 oxygen and 2 hydrogens. They come together and form water. If a hydrogen atom itself, if you look at it up close, consists of 2 parts. This is hydrogen. Hydrogen consists of 2 parts. It has an electron and it has a proton. These are 2 small particles, the electron and the proton. The electron has what we call negative charge, electric charge. The proton has positive electric charge. We're going to be talking a lot more about these. What it means is the electron and the proton attract each other. That's why they make hydrogen. And the remarkable thing about it is the proton is much, much heavier. It's about 2,000, it's actually 1836 times heavier, the mass of the electron. So most of the mass in a hydrogen atom is in the proton. For reasons of quantum mechanics that we're not talking about just yet, what this means is the proton will be confined to a very small space in the middle, and the electron will be in this big cloud moving around. So the electron, sometimes called the electron cloud, some people like to think of this like a planet going around the sun. That's not a bad way to start thinking about it. When we get to quantum mechanics, we'll find that it's really not very accurate either. But the electron going around the proton, because of its heavy mass, turns out has a much more well-defined position. And in fact, this thing is tiny. And here's the analogy. A typical atom is 10 to the minus 8 centimeters in size. And a typical proton is like 10 to the minus 13 centimeters in size. That's 100,000 times smaller. That's a huge difference. The proton is this tiny spot that you'd think it would be hard to find. In fact, it was about 100 years ago that Rutherford discovered this. And it was rather astonishing that most of the mass in the atom is in this tiny little piece. It's called the nucleus. For the hydrogen, the nucleus is simply 1 proton. But if you want an analogy, think of it in the following way. Take a football stadium. Okay, so let's say here's a football stadium. And here's the field. And let's say the whole football stadium this is about 100 yards, say 100 meters. This whole thing is about 300 meters, like that. Not quite a kilometer, a third of a kilometer. Maybe it's not. Maybe it's bigger than that when you're putting all the seating and so on. But let's say 300 meters. Take a mosquito that's about 3 millimeters. So that's 3 times 10 to the minus 3 meters. This is 3 times 10 to the 2 meters. And the ratio of that is 10 to the 5th. And that's the same as the proton in the atom. So this truly amazing fact that it's just that if you want to know what the proton is like in the atom, just imagine a mosquito in a football field, and that gives you the relative size. And yet it's the mosquito that has most of the mass, and that big electron is zooming around out there. But in chemistry, in atoms coming together, the protons just kind of stick in the middle here. They don't do anything except hold the electron in place through the electrical attraction. But all the interaction between the atoms is in that electron. And this is true of all chemistry. All chemistry consists of the nuclei basically just sitting there. And you may be sharing an electron. This electron may be on this atom for a while, and then it goes on that atom. And then it comes back, and they're sharing these electrons. That's one way in which chemistry takes place. So it's all the electrons. And the typical energy is about 1 electron volt per atom. But there is something new that was discovered by Becquerel back in the late 1800s, and then studied by Curie and Rutherford and a whole bunch of other people. And this is the fact that this nucleus, when you think of it, is a positive charge. We actually now know it's made up of pieces called quarks. And if you look inside the proton, which we can do, and we have done, look inside the proton, you find it is not a single piece, but actually consists of 3 things. I don't want to put the bag around. This is really equal to these 3 things called quarks. We know of 6 different kinds of quarks. The proton contains 2 of these. They've been given very unimaginative names because physicists no longer study Greek and Latin, and so they can't come up with exotic names like the biologists can. You know, you learn, like Ursa horribilis, the grizzly bear. What a great name that is. So this thing is called the up quark. There are 2 up quarks and 1 down quark. At least the word quark is an interesting name. The word quark was invented by one of the most literary of all physicists, Murray Gell-Mann, and he didn't really invent the name. He was just, like most of us, we love to go and relax by reading Finnegan's Wake by James Joyce. So he was reading this, and he came across the statement, 3 quarks for a muster mark. And he thought, meh, those must be the things inside the nucleus. So I called them quarks. Now at the same time, another physicist, whose name I can't remember because he wasn't quite so reading the same books, had the same idea, and he called them aces. Well, quarks stuck. So the things inside the nucleus, this nucleus is really 3 quarks, and they're tied together with things that we now call gluons. Again, a very unimaginative name. They are the glue that holds things together, and this is inside the proton. But now imagine the following. These quarks have a charge. If we call the charge of the proton +1 in units of proton charges, then the up quark has a charge of 2/3. And this one has a charge of -1/3. And you add together 2/3 and 2/3 and -1/3, and you get 1. And that's what's inside the proton. This was all discovered when I was a postdoc. I mean, I watched the people. This was not my field at that time, but I was very close to the people who were doing this, and it was really an exciting time as they're figuring out what's inside of the proton. But look at these 2 things. They have positive charge, they repel each other, and yet they're enormously close. Why don't they go flying apart? Well, the reason is these gluons are very strong. You wouldn't want to make up a theory like this. People would say you're crazy. You have to discover it by experimental measurements. But that's what's going on inside. Some nuclei, let's now jump from hydrogen all the way up here to the end. Let's take a look at uranium right there. Actually, all these elements here, there's uranium, uranium-92. Okay. Why is it element number 92? It's a nice story. Uranium, in its nucleus, has not 1 proton, it has 92 protons. So there are 92 of them in here. And the electrons, it has 92 electrons, all going around in different ways. That's why it's called element number 92. Each one of these elements, the atomic number, there's 1, there's 2, helium. There's 2 protons. 3, 4, 5, 6, 7, 8. Oxygen has 8 protons, 8 electrons. Fluorine, neon, sodium, magnesium, aluminum, silicon. It's all the number of protons in the nucleus equal to the number of electrons. Now you could steal an electron off, then the thing is called an ion. An ion is one that has the wrong number of electrons on it. So an ion is like an atom, but it has a charge. But generally, the atom has an equal number. Now, with this, you have all these protons really close to each other. And they're repelling each other. You think they might one day break apart. And they do. And that's called radioactivity. So radioactivity is when the nucleus of the atom explodes. Now, sometimes it happens spontaneously, like these things here. This watch is full of radioactive atoms. Radium. And they're just exploding. You think it would run out. But when you think of the enormous number in here, you can say, well, how long will it take it to run out? A long time. You're hearing maybe 1,000 clicks per second, maybe only a few hundred. It's hard for me to judge it. But there are a huge number of atoms. This is somewhat dangerous because when you have a nucleus exploding, the pieces go flying out. And when they go flying out, they don't have one EV. They typically have, and this is a number I want you to know, they typically have 1,000,000 EV. MeV, 1,000,000 electron volts. A typical atom exploding, the nucleus exploding, radioactivity releases typically 1,000,000 times the energy compared to one atom undergoing some sort of a chemical reaction, like burning of hydrogen. Now, the number isn't always 1,000,000. Sometimes it's 100,000, and for some cases of fission, it's 200 million. But let's just get that number of 1,000,000 burned into your heads. That's the danger of radioactivity. That's the advantage of radioactivity. Now, when these things blow apart, pieces come flying out. The pieces that come out are what we call the radiation. So radioactivity refers to the fact that this thing explodes. Something that's radioactive is something in which the explosions are occurring naturally. But things that go flying out, let's look at this. I don't know if anybody knows what this is. It's a smoke detector. And the best smoke detectors, the ones I recommend you get, are ones that have these radioactive sources in them. We'll explain how they work in a moment. So here's all this radioactivity. Now let me put this can on it. Oh, the can stops the radioactivity. Yes, this is a kind of radioactivity that is basically stopped by a metal can. Let's try a piece of paper. Can you hear that? It stops some of it, most of it, but not all of it. See, this over here, it's not radioactive. Here it is. But if I take away the piece of paper, there is some kind of radioactivity that was, these radioactivities were discovered, they didn't know what they were. These are radiations coming from radioactivity. And they noticed there are kinds that had different properties. Like, let's see these kinds here. Let me put the mic over here. This kind isn't stopped. Put a piece of lead on top of it. Lead is pretty good at stopping it. So some kinds of radioactivity are easily stopped, others aren't. They started giving names to these. They didn't know what they were. They called them, the first one that was found, actually the first one was called X-rays. And then later they found, and X-rays would go through the body but was stopped by the bone. It's really a wonderful historical story of Röntgen, who found this thing and discovered it accidentally. The film was being fogged, so he discovered he could expose photographic film through a wooden box. And then he tried putting his hand there, and he exposed just to see whether the stuff would go through his hand. And he found it did go through his hand, but not through his bones. And he got a shadow of his bones. And suddenly he knew he had something big. He had a way of looking at bones by using the radiation. He didn't know what they were, so he called them X-rays, because X is the thing you use for the unknown in algebra. So they became X-rays. And later on, people found things. They started using letters of the Greek alphabet. They called them alpha rays. The next ones were beta, alpha, beta, gamma rays. Gamma rays go through a lot. They don't go through the lead, but they do tend to go through, but they will go through paper and things like that. So the gamma rays go through paper. They didn't know what these things are. Now we know what they are. And we'll be coming to that. I'll tell you what they are very shortly. Let's take a look at this thing over here. This is not... This is a way of looking at the radiation. And we have that up on the screen now. Maybe turn on the lights, you can see it better. We turn down the lights a bit. Let's see what we can see. This is what's called a cloud chamber. A cloud chamber is a bit of gas. It has air and alcohol in it. And the purpose of the alcohol, it has dry ice underneath it. And what we do is you cool it until it's about to turn into a cloud. And you can see there are little clouds that form now and then. These are just the conditions where there's so much alcohol in the air and it's cold and it tends to form a cloud. And Wilson discovered that when you do that, it tends to form clouds around in little streaks. We now know that these streaks, there's one over there. See that go by? These streaks are actually, ooh, look at that one. That went like that. And then because of a little bit of breeze, it broke up. But what you're doing is forming clouds along these paths. We now know that these paths are paths of radiation. So a particle, radiation, some kinds of radiation turn out to be electrons. Some of it turns out to be nuclei. Pieces of nuclei are, when they're moving, shot out from this nucleus at very high speed. Then they make a cloud form along it. There was a piece shooting out like that. This one is probably coming up, so it looks kind of funny in shape, going that way. And there's a little one there. And you see these things every now and then, little one there. And you see them forming. So what is happening, we now understand, is that when you have the radioactivity, in some cases, the nucleus breaks up, pieces go flying out. The piece could be a fragment of a nucleus, which has protons in it. One of the most common ones turns out to be called an alpha particle. An alpha particle has 2 protons. Another piece that comes out is an electron. The beta rays turned out to have been electrons. Alpha particles have 2 protons. Beta rays so the alpha particles are pieces of nuclei consisting of two protons. They also have 2 things in them called neutrons. Beta rays are these electrons coming out. What happens when they come out? Let's talk about the dangers of radioactivity and what it does and why some of it, why I wear this but not the wristwatch, not this other wristwatch. So I'll get the lights back on. Let's talk about what happens when one of these fragments goes flying out. Yes? Yes. The question is, does that mean that alpha particles are helium nuclei? It turns out alpha particles are identical to the nucleus inside the helium. That turns out to be very interesting. In fact, let me digress on that for a moment while I remember. Because when these nuclei break up, one of the pieces, one of the small pieces that comes out is typically a fragment of a nucleus consisting of 2 protons and 2 neutrons. A neutron is a third particle that's just like a proton except it has no charge. It has no charge, but it does have gluons, and so it helps hold the nucleus together by adding more gluons without having the repulsion of the charge. So a helium nucleus has 2 protons, as I said, but it has 2 of these other things in it called neutrons that just help hold it together. And if they hold it together so well with 2 protons and 2 neutrons that when pieces come flying off a big nucleus, very frequently one of the pieces is an alpha particle, namely a helium nucleus, namely 2 protons and 2 neutrons stuck together. So imagine this explosion, and the pieces come off, and one of these pieces is a brick, a small particle consisting of 2 protons and 2 neutrons. This goes flying off at high speed. It has charge. It has electric charge. Because it has electric charge, whenever it passes by anything else, like an atom, that atom, the electrons in that atom are attracted to that charge. They may be pulled away from their own nucleus. You may turn one of these atoms into an ion. Here's what I want you to visualize. This nucleus blows up. One of the pieces that comes flying out is a charged alpha particle, 2 protons and 2 neutrons. It goes flying through matter. As it does that, it passes by a nice, neutral, happy atom. But the electron in that atom sees this positive charge coming near. It's attracted to its nucleus, but it feels this too. It may get ripped off. And that's typically the damage done by radiation, is that it knocks electrons off atoms. That's the key mechanism. When you knock an electron off an atom, you don't have that atom anymore. You have a charged atom. If you knock one electron off carbon, carbon has 6 protons and 6 electrons. There it is. Atomic number 6. 6 protons, 6 electrons, plus some more neutrons. Typically 6 more neutrons. You knock an electron off, and now you have a charged atom. Not surprisingly, an atom that has charge behaves quite differently from an atom that's not charged. It may be very reactive. Those of you who study chemistry know that ions are very chemically reactive. Suppose it's part of a water molecule, and you knock an electron off. The molecule itself may go flying apart. Suppose it's part of your DNA, the oxyribonucleic acid, the molecule that encodes all of your genetic information and how to run the cell. If you knock an electron off one of those atoms, you can basically break the DNA, put in what's called a mutation. The cell may not function anymore. DNA will come along, and it has these marvelous mechanisms that we've only been discovering in recent years. It has chemicals that actually move along the DNA and look for mistakes, things that were damaged by radioactivity. And it will sometimes fix them up and then move on. But if you get enough of these damaging alpha particles coming by, and they break enough places in the DNA, the cell can just die. Or even worse, if the disruption is just done in just the wrong way, the cell gets out of control of itself. It starts replicating. The mechanisms that keep it from replicating now are turned off. It starts dividing like it did when you were a little baby. And that's called cancer. So the damage done to the cells is by these particles flying by, disrupting the atoms, knocking off an electron, changing the chemistry. At this point, a zillion different things can happen. The nicest one that can happen is it just kills the cell. You get a lot of that happening. Suppose I'm exposed to a lot of radioactivity, and a lot of my cells get killed. Well, I don't need all my cells, but if enough of them get killed, and there's enough damage, I'll die. That's called radiation poisoning. With less radioactivity, not enough to kill my cells and kill me, but it may do some genetic damage. And the one that is probably the most dangerous is to form mutations that will trigger cancer. And so radioactivity yields radiation. The radiation goes through my body. It knocks off electrons. The electrons change the chemistry of the atoms. They disrupt the DNA. The DNA now loses its ability to control the replication. Replication goes wild. We have cancer. So this is how radiation does damage. How much radiation does it take to do these things? Well, how do you measure? These are some of the most important numbers I'm going to ask you to remember. I'll put them on the board whenever there's a number I want you to remember. But these have to do with radiation damage, and you'll find this enormously useful when thinking about nuclear reactors, nuclear bombs, radiological weapons, whatever. So to quantify this, people have asked, well, how much damage is done by a certain amount of radioactivity in my body? And before they understood the mechanisms, they came up with a unit called the Roentgen, named after the discovery of X-rays. And what they did is they say this energy, these particles, are going through, and they're knocking electrons off, and eventually these electrons go off to get the chemical reaction. Most of the energy eventually turns into heat. So all they did was to determine how much piece of water heats up when you put radioactivity next to it. And that way you can measure the danger of radioactivity. Now, it's not the heat that's doing the damage. The heat is a byproduct. But the assumption was, well, it probably is the more radiation, the more heat, and so on, and so let's consider that. That was called the Roentgen. They eventually changed that to the REM. I guess maybe the Roentgen was, they had different ways of doing it. The amount of charge released, the amount of heat released. One of them was the REM, one was the Roentgen, and then they figured out really how much damage it does, and they called that the Roentgen equivalent. You don't have to know all this stuff. Just what I want you to know is that when we measure damage, the unit that they finally came up with was called the Roentgen equivalent for man, which is the REM. And you don't even have to know what REM stands for. It stands for Roentgen equivalent for man. And you don't have to know that because that's unimportant. The thing you have to know is that we use the REM to measure the radioactivity, the damage done to a cell. The amount of damage depends on the number of REMs. Well, REM was really named after Roentgen, and everybody, since Physics for Future Presidents doesn't require you to know that, therefore Mr. Roentgen gets no honor. So let's change the name and honor somebody else, like the head of the committee who's in charge of all this stuff. So they did that, and they created something called the sievert. And the sievert, they decided we're going to make it more relevant for radiation harm, and they'll call it 100 REM. Now here's the bad news. I want you to know that. Sievert, 100 REM. REMs measure the harm done to a cell. Sieverts measure the harm done to the cell. But here are the numbers. How many sieverts do you need in order to see some ill effects? The answer is about 1. That's why it's a useful number. At 3 sieverts to every cell in your body, that has a special name. It's called a whole body dose. So we take 3 sieverts, and not just to my fingertip, but to that fingertip, and to every other cell in my body, we give me 3 sieverts of radiation. That's called LD50. Lethal dose for 50%. LD50. You need to know that term. You'll see it in the newspapers from time to time. If I get 3 sieverts to every cell in my body, meaning a whole body dose of 3 sieverts, these sieverts usually mean per gram, but this is to the whole body. Every cell in my body gets this. Then I have a 50% chance of dying within a few weeks from that dose from radiation illness. This is, I mean, without going into the details of radiation illness, let me just say that it means that the chemistry of my body is so badly messed up that my mechanisms of my body cannot recover. Usually it means you've broken up enough enzymes, they wind up doing the wrong thing. So what is radiation illness like? Anybody here who has a friend who's gotten radiation treatment for a cancer knows, because their friend is basically suffering from radiation illness. It's somewhat ironic that cancer cells, some of which may be caused by radioactivity, most of which are caused by other things, cancer cells, because they're so busy reproducing, they don't have the mechanisms working well to repair themselves. And as a result, this is one of the great discoveries, it turns out cancer cells are more vulnerable to poison and to radioactivity than our normal cells. So maybe by eating a well-done hamburger, which has lots of carcinogens in it, or maybe by bad luck sitting next to radioactivity, or for many other, maybe just some spontaneous changes in your DNA, you get a cancer cell that can't control its reproduction, so it divides into 2 cells. Each one of those has the same DNA, so they start dividing. 2, 4, 8, 16, 32, 64, 1, goes up and up and up, and pretty soon you have a cancer growing, which could interfere with your blood flow or your lymph or all sorts of things. But these cells are specialized in reproduction. They're not very good at surviving poisons. And so two of the main ways of treating them are to fill your body with poisons to the point where almost every cell in your body feels like dying, but the cancer cells die first. That's called chemotherapy. And the reason you feel so miserable from chemotherapy is because you're using this little difference between the cancer cells and the regular cells. Another is called radiation therapy. And so what they do is they hit all the cells in your body, or maybe if the cancer is just here, this is a nice advantage of radiation therapy, you can send radioactivity just to that one part, maybe to the thyroid, if you have cancer, thyroid cancer. And the radiation then causes radiation illness to all of these cells. And the cancer cells tend to be the ones that die. Radiation therapy, again, is very similar to chemotherapy. If you've had friends, and I've had several who undergo radiation therapy or chemotherapy, and you see the symptoms, they feel nauseated. It's really kind of miserable. Nothing I hate more than feeling nauseated. And your hair tends to fall out. And that's one of these symptoms. You'll see them in movies, too, when someone is exposed to radioactivity. They love to show the hair falling out because that's one of the really bizarre aspects of this. But people undergoing chemotherapy and radiation therapy will sometimes wear wigs so that you don't notice. They don't want you to know they're undergoing this because cancer, oddly, is a very common disease, but we treat it as if it's not. I want you to think mentally, just for a moment. What fraction of you in this room will die of cancer? I don't mean from radiation, from my demos or whatever. What fraction of you will die? Just think in your head, what number do you think it is? Is it 1 in 1,000? Is it 100%? Is it 1 in a million? What fraction of people in the United States today die of cancer? I'm just curious. Let me take a quick vote. Okay, so I'm going to have a vote, let's say 1 in a million, 10 to the minus 6, 1 in 1,000, 10 to the minus 3, 1 in 100, 10 to the minus 1, I don't know, 0.2, 0.5, and 1. Okay, so how many people say 1 in a million, approximately? Just raise your hands. Okay, we have, you raise it like this so I can see it, even if you don't want to, you shouldn't look around and see what everybody else is voting. Not too many, just 7. Okay, how many people say 1 in 1,000? Okay, and I get there about 20. Okay, how many people say 1 in 10 die of cancer? Okay, and I'm getting there 53. How many people say about 20%? Okay, and there I'm getting 179. How many people say about half? Okay, we're getting the numbers down here a little bit, so that was 47. And how many people say basically everybody? Okay, and that's 7. Okay. By the way, there's an interesting theorem I learned. You're talking to someone and they quote some statistic. This isn't true for me, but it's true of most other people. The fact is that 87.3% of all statistics are made up on the spot. Okay. Anyway, you're right. It's about 20%. And yet, there's a stigma associated with it. Maybe you don't want people to know you're going through this misery because then they treat you differently. You get really tired of people saying, oh, I feel so sorry for you. Okay, that's nice the first day, but after a while, you just want to get your normal life back. And cancer patients, there are probably some people here in this room right now who are undergoing treatment for cancer. And they probably don't want you to know it. Just because they want, you really miss your normal life when something like that is happening. So about 20% of us die of cancer. Now, 3 sieverts are enough to give you basically LD50, 50% chance of dying from radiation illness. If you get up to 10 sieverts, you'll die real fast. 3 sieverts probably take several weeks. There are these stories of people who suddenly realize they'd been exposed to radioactivity, and of course they don't feel anything right away. But they know they're going to die within a few hours. So it's a strange thing. You don't feel it right away, but your chemistry has been disrupted. Now, as it goes up a bit, Now here's one of the oddest facts you're going to learn. This is one that you will have fun with. Some of you are physics majors, but you'll have fun with physics majors, with biology majors, with everybody else over this one. It's a real puzzle. Here's the question. To have a 50% chance of dying from cancer, how many sieverts do you have to give my body? Just no treatment. 50% chance. How many sieverts? The number's a little bit controversial because we don't do experiments like this. We do them on kittens and puppies and things, but not on people. Anyway, the answer turns out to be approximately, and this is a little bit disputed, but not very much, about 25 sieverts per cancer. There it is. 25 sieverts is one cancer. Ten sieverts will kill you within half an hour. That's the paradox. How can you ever get cancer if the radiation kills you first? This is an important thing for you to know. The answer is you can. How? Well, 25 sieverts will give you cancer. 2.5 sieverts will give you a 10% chance of cancer. That's called the linear hypothesis, and I want you to know that term. There's no more important term for you to know when discussing radioactivity than the linear hypothesis. And there are several ways to say it. One is 25 sieverts equals one cancer, approximately. 2.5 equals 1/10 of a cancer. What does that mean? Does that mean you only have 1/10 of a cancer? No, it means that you have a 1/10 chance of getting cancer. Because the way cancer works is you're going to disrupt fewer cells with a lower radiation. Will one of those cells be disrupted in such a way to form cancer? Your odds are, well, with 25 sieverts, you're getting all this dose to your whole body. Yes, on average. Some people won't. For 1/10 that dose, your odds of having that particular damage that triggers the cancer is 10 times less, but it still might happen. Suppose we go down to 1 sievert. Then the chance is 1 out of 25.